Hello everyone. Today we will discuss Leetcode weekly contest, I think 349 and maximum sum queries. So it's a hard problem and we are currently in the contest only. So the problem says that you are given two arrays. You are given two arrays n1 and n2 and both of them have some elements and they are of the same size. And you are given some queries. So you are given queries of the form of uh, v1 and v2, and for each query let's look for example this query of 3 comma 2. You need to find, you need to look at all the pairs in the two arrays such that um, if you look at these pairs, the positions at the same index. So for example in 3 comma 2 we need to look at all the pairs where the nums1 of I is greater than equal to 3 and num2 of I is greater than equal to 2, and out of all these pairs we want to return the pair with the maximum sum. So for this query, one pair will be this, another pair would be this, and the maximum sum in this case would be 9. So let's just look at the test case. So we are having 3 2 5 2 3 and 4, and there's a query from 3 comma 2, and the answer to that is 9. So how do we solve that problem? The first intuition that might come in your mind is, what if we sort the arrays, sort both, we can create a vector of pairs, um, and we can sort that pair, and then maybe we can do something with it. So because the indexes, the n1 and n2 values, we only look, we only care about the values which occur together, which occur at the same index. So we can create a vector of pairs. So suppose we now create a new um, vector of pairs out of the two arrays, and this is how it would look. And we have these queries, right? Queries of the form of x and y, and maybe we can sort this. Vector based on the first key. So it would look something like in this case 2 comma 3 3 comma 2 and 5 comma 4. Okay, now suppose a query comes for x and y. um, in general the array, the sorted vector will look something like this, right? x1 y1 x2 y2. In this case this looks like this, but it will look something like this. Suppose a query comes for some x comma y. So we need to look for all the pairs where xi is greater than equal to x and yi is greater than equal to y. So in this sorted vector, we can do a binary search, and suppose this is some index k, which is the first point where xk is greater than equal to x. So all the pairs ahead of this will fulfill the first condition because it's sorted on the first key, and um, but we cannot say anything about y. So we will still need to maybe iterate this portion manually, and then look at only those pairs where y j is also greater than equal to this query, because the sorted vector is sorted based only on the first key, not on the second key. So it could look something like 1 2 uh, 2 3 and 3 maybe 0. This is how it could look. It's sorted on the first key, not on the second. And if a query comes maybe for 2 comma 1, that means we want to look at all the pairs where the x is greater than equal to 2 and y is greater than equal to 1. We will do a binary search and we will know, okay, this is the limit where we need to search because these are all the points. Anything before that has x value less than 2. Um, but in this segment, we cannot just directly, we cannot say anything directly because if you compare these two pairs, here y is 3, here y is 0. So y is not sorted. So thinking in the direction of binary search is a good place to start. But if we want to you know, have a solution only using that, so in that case, the complexity will be order of log n into, I think, um, each query will take n time and then it's q. So it's because you're binary searching um, on the partition where the answer may lie. That will take log n time, but then you're again iterating over this entire range to look at the y pairs. And then we have q query. So this will definitely TLE. So we will continue in this direction only. So we have, let's say we have sorted this array based on the first key, the input array. Now what we can do is we want to actually convert this problem into as many, we want to add as many constraints as possible, so that we want to basically control as many things as we can. So in this question, if you see, we are given the queries in advance. We are given all the queries. So x val 1, y val 1, x val 2, all the queries, all the q queries, they are given in advance to us. So maybe uh, we can use this fact that these queries are given in advance, and we can we don't need to actually answer them in this order only. We can answer them in whatever order we want, and we can later reorganize our answer. Maybe we can answer the third query first, and then the second query after that, and then finally we will have a answer array, right? So we have to just return that answer. It doesn't matter how we are calculating it. So what we will do is we will also sort this query array. Okay, we will also sort this, and we will sort this on the basis of decreasing x value. So we will sort this query array based on decreasing x value. Now let me just take an example from the sample test case, and I will just quickly show you that. So we will take this first example only. We are given the two arrays like this, 2, 4, 9, 5, and we have made a vector of pairs. We have now sorted this, so we get something like this. I think 2, 5, 3, 4, and 4, 2. Okay. So and then we are given these queries. The queries are 4, 1, 1, 3, and 2, 5. 1, 3, and 2, 5. So what I'm saying is that instead of answering the queries like this, let us sort the queries based on decreasing x. So we will sort the queries based on decreasing x, and how that will look like. The new query will look like 4, 1, 2, 5, and 1, 3. You can see the x value is decreasing here. The y value we will handle that later. Now what advantage does it give us? Suppose you are trying to answer this query. Okay. In this query, you are concerned with those pairs where the x value is greater than equal to 4. Okay. So that will be just this pair, correct? Only in this pair. Y value we will look later. Okay. Y, we are not concerned about y right now. Now, when we are answering the next query, suppose we are answering 2, 5. We are only concerned about those pairs where the value is greater than equal to 2. So what will those pairs be? These will be those pairs in the original array, like in the original sorted array. And then finally, this is a 1, 3 query. So then the entire array will be used because all the array x values are greater than equal to 1. So you can see that the segments that we are concerned with are increasing segments, because here because for the first query only the last element of this array was needed. For the second query, the last three were needed. For the last three were needed. For the third query, the last four will be needed, because as you you're sorted it in decreasing order, right? So after this, if a query comes, it will have a value either less than or equal to the previous x. And if you look in terms of the original array, that will mean that uh, the window size that we are concerned with will increase. So the advantage here is, suppose like in this, like I said, in here we will only concern with the last query, and then here we will concern with the last three queries. So we just need to add these two values to some data structure that we are creating. This value was already stored before in the previous query, so we don't need to repeatedly add every element of the vector will be added only once as the size of this uh, window increases as we are answering more and more queries. Okay, this is what I wanted to say, that this is why we are sorting the initial array based on the x values, and we are also in descending order we are sorting the queries, so that one by one when we are answering the queries we can reuse the previous information. Okay, I hope this much is clear, the intuition of why we are sorting it like this. Now I will now move to the actual final solution. We will continue with this test case only. Let me remove this writing. All right, so now what do we now we need to worry about the x part is handled, right? At least the x part is handled because one by one we are increasing the window size, and we know what all segments we are concerned with. But the y value is something um, that we don't really know anything about. So this will need some prerequisite knowledge of segment trees. But before segment trees, I will explain it in another way. Okay, what we will do is we will maintain a vector. Okay, vector will contain information about all the pairs that have been processed so far. Information about all the processed pairs. Okay, this will be a segment tree later on, but if you don't know segment tree, I will explain with the vector for now. Okay, so we first look at the first query. Okay, it's saying you find all the pairs where x value is greater than equal to 4 and y value is greater than equal to 1. Initially our vector will be empty. We will have an index at the end. Okay, this will be our index. So this is a potential candidate which can be added to the vector. We will check, is the x value greater than equal to the query's x value? It is. So we will add that information, and we don't really need to add the x value because um, you know, I mean, it's not needed, but let's suppose we are adding it. So we will add this pair. We will add 4, 2, and we will add the sum. Sum is 6. Okay. We will move our index 1 position to the left. We will check. Uh, Basically, we are trying to add all the new possible candidates for a query. Now, we look at this. We look at, okay, say x value greater than equal to 4. No. So this candidate will not be added for this query. And any candidate afterwards, this will also not be added because for that the x value will be less than equal to 3 only. So it won't be greater than equal to 4. Now we only have one element. Now to answer this query, we will look in this vector. These are all the good vectors. And we will only look at now those, you can sort this on the basis of y. Or you can initially you can just iterate over this vector and you can only look at those pairs where the y value is greater than equal to 1. So in this case there's only 1 and the y value is greater than equal to 1, so your answer will be 6 for this query. Okay, now you move to the next query. So this has been answered as 6. You move to this query, which is I think 2 comma 5. So you will check, let me confirm it's 2 comma 5 or 2 comma 4. It's 2 comma 5. Now you look at this 2 comma 5. So you will add all the vectors where x is greater than 2 and y is greater than equal to 5. So look at it like this now. This vector 4 comma 2 will definitely be added because, I mean, on the basis of x, because its x value is greater than equal to 2. But we don't need to add it because it was already added in the vector before. Our idx was moved here. So we will only look at this element where it is pointing to right now. So we will look at its x value. It is greater than equal to 2. We will add it. We will add it. So we will add 3 comma 4 comma 6 comma 7, which will be the sum. We will move our idx here. We will look at the we'll compare the values, and here also the x value is greater than equal to 2. So we will again add it. So we'll add this pair. So these are basically all the potential pairs, but we have not yet checked the y value. Okay, and then we will move here. So you are only adding any element one time only. So the total complexity will be, I think, order of n only for adding, and then for answering each query there will be some complexity as well. We will look at it later. Then you look at this element, it's a 1, and this 1 is not greater than equal to 2, so this won't be added, but it will be a potential candidate for later on. Now in all these elements, you will now look at these elements, you will look at only those elements where the sum is greater, where the y value is greater than equal to 5. So this element won't be considered, this element won't be considered, only this will be considered, but they will not be removed. They are still potential candidates later on, because it's possible afterwards there a query which has a very low y value, maybe 1 comma 0. So I mean these candidates will be useful for later on. So this is the only one uh, which fulfills the criteria, and our answer will be 7 for this query. Now again we are here 1 comma 3. We are going to add, um, we don't need to re-add these values. They are all good potential candidates based on the x value, but not possible, not necessary on the y value. So we will add this. It's like 1 comma 9 will be added with the sum of 10, and uh, then you will look at all these pairs again, and you will only look at those pairs where the y value is greater than equal to 9, and only this pair will suffice. So in this case, the answer will be 10 for this query. I think this is how the answers are looking. Yeah. And this is in another order. This is another order because the queries were jumbled. You can then reshuffle the queries. You can also store the index of the original query, and then you can sort based on that. So we have now the only bottleneck in this solution is how do you quickly check in this vector. This vector contains all the pairs where the x value is greater than equal to the threshold for the current query. But the y values again, it's not sorted actually. So you need a better way than iterating over this vector again, because if you do that, then the complexity is again order n square. So how do you do it? Well, the answer to this is I maintained a segment tree. So suppose in this case we will um, the maximum value of y is 9 over all the arrays and all the queries. So I will maintain a segment tree of size 9. So it's like index 0, 1, 3, 4, 5, 6, 7, 8, 9. And whenever a new entry is added to the vector, I will simply update that y index with the sum. So initially, if you remember, initially this pair was added, right? 4 comma 2 comma 6. So at y equals to 2, I will update the sum as 6. Then this element was added later on, 3 comma 4 comma 7. So at y equals to 4, I will update the sum as 7. And then you remember for this only, for I think for this query only, this was also added 2 comma 5 comma 7. So at y equals to 5, I will update the sum as 7. Now suppose I wanted to answer this query 2 comma 5, right? 2 comma 5. I will look at my segment tree at that point, and I am only concerned with all the pairs where the y value was greater than equal to 5. So I will do a range query in the segment tree in this region. And if you know segment trees, you know this update operation and all that is very simple. You need a simple segment tree. You don't need a lazy segment tree here, because we have point updates and range queries. So, and you can just do an update here. Okay. Um, and that is how you will reduce the complexity. So in each, what will happen is while answering each query, you will do two things. Suppose you want to answer this query 4 comma 1. You will first of all move the candidates from the original array to this set, or I mean you don't need a vector at this point, but you will move it to this vector. You will then update the segment tree, so that will take log n time, and then you can simply query the segment tree on the range from y to the maximum y possible value. So the complexity will change from order of n to order of n square to order of n log n. N is because we have to add the queries to the segment tree. Each query will be added. So there are n queries, and this is the time to add it, log n. this is how you will do it, but there is one small thing that you need to worry about, and that is the value of y can go to 1 e to the power 9. Um, so you cannot make a segment tree that big. So for that you need to do some coordinate compressions. The thing to note here is, if you know coordinate compression, you can, I think, end the video now. But if you don't, I will just quickly give you a brief idea. Suppose the y values, suppose the queries were like maybe 1 comma 1 e to the power 8. Okay, so you would need to do a range query in the segment tree from 1 e to the power 8 to maximum y value, whatever the maximum y value will be. But you cannot make an array of such a big size, right? So what you can do is you can convert. See, you are not actually concerned with the actual value of y. You are only concerned about the relative ordering, because it says that you have to answer queries where y is greater than equal to something or y is less than equal to something, whatever. So you if you are only concerned basically with the relative ordering, not with the actual value. So suppose, how do you do coordinate compression? Suppose you had an array like 0, 5, and 3 and 6. You will convert this to a shrunken range of size n minus 1. So of size n, and basically you can if you sort the array will look like something like 0, 3, 5, and 6. So 0 will be given an index 0, 3 will be given an index 5, 5 will be given an index 2, and 6 will be given an index 3. So your array will look like 0, 2, 1, and 3. Um, the Both the arrays maintain the same relative ordering. So index 0 is less than index 2 here. Index 0 is also less than index 2 here. And you're only concerned with the relative ordering in the segment trees. Uh, in this case, you're not concerned with the actual value. So that's why this coordinate compression will work. You need to only do coordinate compression on y, because that is being queried in the segment tree. And a question might come to your mind that, hey, if you're doing coordinate compression on y, won't the sum change, because sum is xi plus coordinate of yi. Uh, so no, this will not change. Actually, you want to update, um, the segment tree with the sum, right? This update value can be as large as possible. So you will update it with the original xi plus yi only. Only the index of the segment tree or something where the size becomes an issue, and that's where we are applying the coordinate compression. So I will show you the code um, once, if this part is not clear. Also, you need to consider all the y values which were present in the nums2 array and the queries. Okay, you need to consider both of these y values while applying the coordinate compression. Okay, just to quickly summarize the solution, what you're doing is you're number one, sorting the queries based on decreasing x. You're also sorting the input array based on increasing x, so that you only have to add things once to the segment tree, and you will answer the queries in decreasing order. So you will add um, the pairs from right to left, and only some new pairs will be added every time. The old ones have already been added in the segment tree. You will apply coordinate compression, plus you will use some segment trees to answer the queries. So this is how the code looks. This is a normal segment tree code. So what I've done is I have stored all the queries. The first, this is the x value of the query, this is the y value of the query. This is the actual index where the query was present originally. So I am making this query array. I'm sorting that, and I'm sorting that, you can see, based on this is ff is first. So this is a of x is greater than b of x. So you're sorting it based on the decreasing order. Okay, then I need to apply coordinate compression. So I'm looking at all the y values in nums2 and all the y values in queries. I added that to a set, and maps towards the coordinate compression values. And this is how I'm applying coordinate compression. Then I'm making a segment tree on the compressed coordinates. I'm making a vector of the initial nums1 and nums2 pairs, and I am in that pair pushing the nums1 value, the nums2 value, and the sum, because I need to update the segment tree with the sum, original sum. Then I'm sorting it based on increasing x. Then I'm answering each query. For each query, I am adding, like I said, I'm decreasing that idx, right? Where it is, I think somewhere here, right? I'm decreasing the idx. I'm adding new elements to the segment tree. So basically, if the unadded elements x coordinate is greater than or equal to the query's x coordinate, you will update it in the segment tree, and you will update it at the coordinate compressed index of y, um, and you will update it with this value, which is the original sum, and then you will just do a query. You will do a query um, from the compressed y coordinate to the maximum possible y coordinate, which are all the pairs where the y value is greater than the query y values, and you don't need to worry about the x coordinates because you're only adding those x coordinates to the segment tree whose value is greater than x value of the query, and then you are updating the answer, and then you are returning the answer. Thing to note here is that we have originally jumbled the queries, so we need to make sure that the answer is being updated at the correct position. I know this solution was maybe a bit long, but if you know segment trees and if you know coordinate compression, you might have solved problems like this before. Hope to see you in the next video. Bye bye.